mission, maybe I'll shout out loud. Or sometimes, just sometimes I shout out loud, so to keep it irregular and then wake you up sometimes. And so the idea here is to discuss a little bit of magnetars. I apologize to the organizers because I was scheduled to speak on Monday, but I had a problem at the Institute. There was some homage to some people into a lab that I wanted to participate. And so the talk was closer to, in terms of theme, to the topics of Monday, but they kindly let me speak today. So it's kind of a change of gears here because I'm going to talk about magnetars. Very simple version of magnetars. I'm not an expert on any of these things here, so I'm just putting these fun things together. But the idea is to talk about strange magnetars, or quark stars who are very highly magnetized, and also admixed with fermionic dark matter. So I'll go not too much in detail about the dark matter part because it's mostly the part mostly related to the workshop here is the magnetic part. But these things are going together in the subject that I'm describing. So it basically came up because of a question I had to myself, and it was that, so what happens when you have dark matter in compact stars? And so a few people had addressed this question already. And then I thought, so what happens if I have like a quark star or a strange star? And then some people had already addressed this. And so I thought, so what about a magnetic field? So what happens if I add a magnetic field? Does it compete with dark matter? Does it go in the same direction? So what happens, right? And apparently nobody had really asked this question. So I decided to do it in the simplest fashion, right? Just to get some pictures. So what I'm going to present here is very pedestrian and very simple. So the idea is the following. So dark matter is very hard to probe, as you probably know. So I'm going to step a little bit in this direction so that I can see my own slide here. So it needs extreme gravitational interaction so that you can have some hope to detect it somehow. So in principle, these dark matter particles could collide with neutrons. I mean, this is a very small cross-section, but still they could collide with neutrons and other components of neutron stars, which I'm thinking about something much richer than purely made of neutrons. They could be made of a lot of stuff, and then be gravitationally trapped and accumulate in their cores. So it can take some time, but neutron stars live for a very long time, so there is time in principle. So in principle, you could be like accreting dark matter like this in this very simple picture here, which was presented by Kuvaris. I don't know if they have the picture, but they discussed this in some detail in a paper long ago, right? But just a caveat here that I noticed recently. So there's a paper by these people in 2021 saying that like nuclear interaction. So this is all for free case, right? So free usual matter, right? Neutral matter. So if you include nuclear interactions, so not a Fermi gas, not an ideal Fermi gas, plus momentum dependence of the hadronic form factors, then there is some significant suppression, according to these people, of the capture of dark matter by neutron stars. But from my point of view, I don't care here. So I'm just focusing on the possibility of having dark matter by some reason in compact stars and what would be the modifications that this would bring, right? So in principle, for very high densities, one expects to have either hybrid stars, like neutron stars with a quark matter core, as has been studied by many, many people over the years, or even more exotic objects, such as like strange stars, like quark stars or strange stars in general. So if quark stars are to be found in the universe, they probably had some accumulation of dark matter. That's my starting point here. And so the question would be, so what is the effect of the presence of cold fermionic? So it could be fermionic or bosonic dark matter, but I'd like to make stars out of these guys too. Then I want fermions because I want some Fermi pressure in these guys. And so what would be the effect of cold fermionic dark matter on the structure of quark stars? So for instance, the mass, the radius, and so on and so forth. On their stability with respect to radio oscillations. So are these guys going to become unstable? And on the effect on quark magnetars with very high magnetic fields. So these are some questions I'd like to address here. So then come the question, so what do you need, right? So what are the ingredients that are necessary for us to try to answer these questions? So of course, the first ingredient we need is the equation of state for both cold dark matter and cold quark matter, right? And then we have to compute the stellar structure from the so-called TOV, Tolman-Oppenheimer-Volkoff equations for two fluid stars, because you'll have usual matter, baryonic matter, and dark matter. Then you'll have the pressure plus TOV, and then you compute, for instance, a mass radius diagram and whatever you want for this physics of compact stars. Then the second step would be, so what about stability? So then you have to solve the stability equations and see what is the behavior of the fundamental frequency. If you look at the fundamental frequency, when it goes through 0, then it becomes imaginary. When it becomes imaginary, things explode or implode, right? Because you have e to the I something, which will have an I too, so it's going to blow up or collapse gravitationally. So then one has to look at essentially the fundamental frequency and how it behaves when you add dark matter. And you can also ask these questions with respect to the magnetic field and so on. And then finally, the incorporation of the large magnetic fields in the equation of motion for the quark matter, right? So dark matter is not going to see this, and this is not going to affect not the evolution, but the structure equations of general relativity, which is another discussion, right? So something for another time. Okay, so then the equations of state, I'm going to be very simple, and so I'm borrowing the results from these people here, and the assumptions are the following. So I'll have self-interacting cold dark matter, right? And there will be two possibilities. Either they interact among themselves, I mean, these dark fermions, or they don't. Or they interact very weakly or very strongly, right? They basically here don't interact with usual matter. The interaction with usual matter is just assumed so that you can accumulate these guys inside compact stars after like millions or billions of years. I don't care. But the interaction is very, very tiny. So the cross-section is ridiculously small. So I don't have to care about this. So then I have a Fermi gas plus two-body self-repulsion between the fermions. Then I can define some useful dimensionless quantities, which is like the Fermi momentum over the dark fermion mass. And I'm going to consider several values of the dark fermion mass, basically because we don't know the dark fermion mass. We don't know what dark matter is, and so on. And another dimensionless quantity, which is this y, which is, again, the dark fermion mass over the mass scale related to the interaction, right? So it's either strong or weak interaction inspired that you have there. Strong and weak in the sense of like QCD and electroic, but inspiration from that, right? So then I'm going to consider two extreme cases, which are usually considered in the literature, which is weak dark matter, so this guy is small, versus strong dark matter, when this guy is large, right? So it's 0.1 versus 1,000. And then the pressure normalized by the square, the fourth power of the dark fermion mass has this form here, which I ask you to believe it can be computed like this. So the effects from the dark matter self-interaction can be seen in this comparison here, just to give you guys a feeling, right? So if you have free dark matter, so just dark matter, nothing else. So I'm going to build a star just made of dark matter. There's no neutron, nothing, right? And then you can see that the mass is pretty small, ridiculously small, and the radius is also small. But if you include self-interactions for the dark matter, it grows significantly, right? Both the mass and the radius. So this is one of the effects that the self-interaction will bring here. And so for cold quark matter, I'm going to use the simplest and crudest model there is in the market, which is the bag model. Yeah, sure. Go ahead, Kenji.
So you're that much a variable?
Say it again?
You're that much a variable?
No, it's just fermionic. It doesn't interact with regular matter. Just fermionic. It's not regular matter, right? And
Sorry, what you mean is that it interacts gravitationally plus?
yes. No. Interacts only gravitationally with regular matter, with baryonic matter, and interact among itself in this way. Yeah, this is very important. Otherwise, it will mess up every interaction that is happening. So the only interaction between usual matter and dark matter that is implied here is gravitational. Just this. There's an assumption that there is some very tiny interaction just to form this guy, right? Just so that you can accrete this guy somehow, right? And then I forget about it because it's tiny, so I don't care, right? And then for cold quark matter, I'm just going to use the MIT bag model just for simplicity, right? Is it correct? Is it good? No. But it's simple, and when one can compute things, and then see what comes about, and then try to do something more sophisticated, which I'm not going to do today. So then you're implementing, so everybody's familiar with that, asymptotic freedom and confinement in the crudest fashion, right? It's just bubbles of free quarks, essentially. And so you have a dependence on this phenomenological parameter, which is the Beck constant, which I choose a value here essentially to surpass the 2 solar mass limit. So I can make 2 solar mass stars because they are there, right? I don't have to be very strict about this because I don't trust too much the numbers that will come out of this. But just for, make people happy, right? It's, oh, you have 2 solar mass stars and everybody's going to be happy and follow the talk, right? So the pressure, yeah, otherwise they showed, oh, the maximum mass is 1.4, then forget about it, it's all wrong. I can always get 2 solar masses with this guy, right? But I'm not very attached to that. That's what I'm saying. But if you choose this, then the guy without any dark matter or magnetic field or anything will have like 2 solar mass stars. And so the pressure is very simple and has this form, as you know. So there's, of course, dependence on the choice of the Beck constant. And this is a little more complicated because there's some other corrections to the Beck model here. But just to show you that you can get like 2 solar masses more or less easily if you want. And just to give you some picture, so from the TOV equations, which amount to what? So a few things. So Einstein's GR field equations plus spherical symmetry for simplicity, plus hydrostatic equilibrium, just this. So if you do this in GR, so if you go to Weinberg's book or whatever GR book that you like, you'll end up with this pair of equations here. And this is not a closed system. You need the equation of state, right? Because you have to tell what the star is made of, right? Can be made of protons, neutrons, or ping pong balls, or whatever. You have to say this is made out of something. And this is the equation of state, which is going to close the system here. And then you have just to integrate out. It's essentially Newton's result plus GR corrections because pressure and energy density also generate the gravitational field. They're also sources of the gravitational field. And then you can see that depending on the kind of mass that you put here, you end up with very different total masses and total radii, and so different kinds of compact stars here. Okay, so then let's look at the quark stars that mix with dark matter. And then in this case, you have to consider like 2 fluids, right? So you'll have to solve the TOV equations for 2 fluids. And these guys are going to be a couple gravitationally here. So one has to solve this a little more complicated system here with boundary conditions in usual fashion. So the star finishes this surface, usually the pressure vanishes, and so on. And, And then if you want to compute the radio oscillations, something I've done with Jose Jimenez, who is somewhere. Yeah, I can see him there. So he did most of the calculation here. So you can compute, these equations here to see what is going to happen, as I said before, with the fundamental frequency. And then you'll know if your guy is stable or not, or if it is going to collapse, right? And then we're going to see how it depends on the amount of dark matter you put in and on the mass of the dark fermion, and so on and so forth. Okay, so some results for the structure and stability here. So I've done this with a master's student, and now he's a PhD student as of this year. And I'm showing results for this specific mass here, which is related to the neutralino. It's just one example that shows well. And so here the mass normalized by the solar mass as a function of the central energy density, right, in MeV per Fermi cubed. And so what you can see is that the mass itself, the maximum mass, doesn't change too much, right? So it's not a big effect at all. What changes here is the central energy density. So the stable configuration, that is also reflected in the analysis of the stability, tend to go in the direction of higher densities, right? So the first thing that you see here. So here's the free, and here's the self-interacting dark matter, and you see that the effect is larger, right? So the increase in dark matter central energy density for these different lines here, I'm increasing the dark matter central energy density that I put there, does not change very much the mass and radius, right? But it shifts the curves towards higher energy densities. So the range of stable configurations occurs then at higher central energy densities, which is some physics going on, which is very hard to measure or observe in terms of astrophysics, right? And so a slight decrease of maximum mass, as you can see here, as you increase the dark matter central energy density. I'll show a nicer plot than this later, at least for for magnetic field, yes. So some results here for different values of the dark fermion mass. So then structure and stability, that's what I'm talking about here. So then I'll show just 2 slides. I have like 40 plots or 40 panels like this, my paper with more figures in my life, right? It's lots of plots because it depends very much on the mass and so on. So I chose just a few of them to show you what kind of thing is happening, and because it's visible here, in some cases it's not even visible, right? So for the weakly interacting dark matter, so the case with y equal to 0.1, and I'm showing two mass cases here, as you can see here, there's 2. And you can see that the mass radius has visible modifications for small dark fermion masses. So these guys are small dark fermion masses. They go up to 500, right? And so you can see it changes, right? Like this. It moves to higher densities, right? Like this. Same thing here. Here it's almost invisible already. If you look for the fundamental frequency, which is this guy, which I'm plotting versus the central energy density and versus the maximum mass, so you have something different. So it goes in this direction, so it goes to higher energy density. So it opens the window in the direction of higher energy densities, allowing for configuration with higher energy densities that wouldn't be possible before. And it goes to smaller masses, right? So there's a stability window of these ultralight quark stars. This has been also observed by Jürgen Schaffner, Bilic, and other people, a lot of Tolos and so on. And I mean, very, very light stars, so to speak, depending on this mass here. So these guys are like dark, strange planets, which are a very funny name, right? But that's what they are, right? Because they're the size of like Jupiter, right, in terms of mass, and they're strange, right, because it's strange quark matter, and they are dark because there's dark matter, so there's dark, strange planets, which is good to sell probably, and also strangelets, right? Okay, so this is something new, right, that is happening here. And so if you go to the strong case, where the y is now 1,000 instead of 0.1, and I'm showing results also for masses of 1 and 10, then again, modest results for modifications of the mass. The radius is the same. So the radius also changes, but it doesn't change appreciably. So both the total mass and the total radius are mildly modified, right? So the same thing as before. And as we increase the dark fermion mass, I'm not showing this here, but I have plots if anyone wants to see afterwards. The fundamental frequency is strongly affected, right? So if you go to higher values of this mass. So the increase in dark matter central densities, the maximum quark matter central densities can vary up to a factor of 20, which is not small. So the energy densities, central energy densities are very much affected. But the results are very sensitive to the dark fermion mass, which is, I don't know, bad or good, not clear. It would be good if we could put some constraints on dark matter, but they're not strong enough, in my opinion, to put some constraints on dark matter. Okay, so much for just dark matter. So let's talk about magnetic fields. So some effects from magnetic fields, so I don't have to preach to you that it's important and so on. And so since like 20 years ago, it's been discussed that magnetars might reach values of like 10 to 18th Gauss. And so what happens if you take quark magnetars and you compute the equation of state is that, so I'm going just up to this value here, this maximum value, because then I would have to include the effects from asymmetries that I didn't want to. And it's too large if I go way beyond in terms of astrophysics, right? So it's shifting the equation of state in this direction, and so it's shifting the mass radius relation in this direction. So this mass radius is like this, only because it's a pure quark star. So I'm not matching this onto a hadronic star. If I had, it would do something like this and go down here and to the right, right? But I'm considered just a pure quark star for simplicity.
Are you assuming that magnetic field is constant in
Yes, yes, simplest thing possible.
But you are following the Maxwell equation, right?
Say it again?
You need to solve simultaneously the Maxwell equation.
Yeah, I mean, nobody really knows what the field is. So I don't believe any model for the field so far. Some people include like density dependence and so on and so forth. I don't believe any of this. So it might be true, but it's not constant. Yeah, definitely. So I'm just taking the simplest thing possible, and I'm not trying to model like this dynamo and so on, because it's complicated. So it's an open problem in astrophysics, and so I'm not addressing this open problem in astrophysics here. It's just the simplest thing possible. And so, so then magnetic fields tend to pull in the same direction as dark matter, as you can see from here, right? So larger central energy densities, smaller masses, right? So this guy is for no dark matter, the red curve. So if you look at this one, this is what's happening. It's moving to the right again. So there was no concern, as I said before, in producing two solar mass stars here, which is possible if I wanted. OK, thanks. It's really fun. I mean, it really calls the attention, right? Because it's, yeah, very good. And it's very mild modifications of the mass here. So then you can also compute like the compactness, and it also changes just a little bit. But then again, everybody moves to the right. Here it moves a little bit down, but still small effects in the compactness. But we didn't expect anything much different from that, because the radius is not changing that much, and the mass is not changing that much, and the compactness is like the ratio between these two guys. But it's useful to compute it to see what comes out. And then there's this. And you can compute the decrease in the total mass as a function of the fraction of dark matter here in the presence of a magnetic field. And this is a little more interesting, right? So you can see that it goes down as you increase the fraction of dark matter, but it goes down differently for different values of the magnetic field. So it's kind of hard to see here, but you can look at the slope of these curves here. So it's coming from minus 3.6 to minus 2.1, which is non-negligible, small but non-negligible. So something is happening in the presence of the magnetic field for, the total mass as a function of the fraction of dark matter. And there are other observables. This is preliminary. This is something we're doing now with Jose, who is here, and with Osvaldo Ferreira, who is in Rio, my student. And so the radial profiles, this is no surprise. There's no dark matter here, just a magnetic field. So the radial profiles change, of course, right? Because you're increasing the central energy density, right? As I showed before in many plots. So this is not unexpected. So if you normalize everybody by the central one, then the profiles look like this. So you're moving in this direction. So you're like squeezing a little bit this energy density profiles. And if you look at the tidal deformability, then it's more interesting, because then the results are not so small. And this was my expectation by no reason, right? But I expected the tidal deformability would be better, more interesting by some reason. And then you can see that the modifications are more significant. So this is the dimensionless version of this. And you can see the numbers here. So it can change by a factor of 2, sometimes a factor of 3. So it's interesting. And this is an observational result from LIGO Virgo, their estimate for the tidal deformability with error bar, just for a comparison. I'm not implying anything here with this comparison, just showing this, just to see that where's the ballpark, right? I'm not implying anything that is good or anything like this. Don't expect it to be good, right? Just a ballpark of what one should expect. And so there are more observables on the way. So my time is probably almost up. But we are computing a few other observables, and this should appear soon. So I'll just go to my summary and outlook. So the first thing is that we've investigated these effects from weakly and strongly self-interacting dark matter on the structure of quark stars for several dark firmament masses, right? And it depends a lot, unfortunately or fortunately, I don't know yet, on the dark firmament mass. So the results are very sensitive, as I just said. So in most situations, this central quark matter, almost all situations, it is increased by the presence of dark matter. This is basically because you have this extra gravitational pull, right? So you have to account for that. Then you have like denser systems that will push back and keep the star there without imploding. And so other effects are usually modest, in my opinion, right? So if you have strong magnetic fields, they affect significantly density profiles and the tidal deformability. As for total mass, radius, and compactness, not so much, All right, so the effects are very, very minor, I would say. So the next steps would be this new observables. This is coming very soon. Then using some more decent equation of state. So cold and dense perturbative QCD could make, combine with something for lower densities to make a hybrid if we want, make for something more reasonable here. There are several results without magnetic fields, which I have already, but I mean, it's not out yet. We could include also the magnetic field. So I had a master student who did a few of these things. And could do hybrid stars and include the magnetic field on the TOV, right? The effect of the magnetic field in the GR dynamics, which I didn't do, okay? So with this, I'll just stop and thank you for your attention. I think I was on time.
Simple physics picture, I try to understand when you have these two components, regular matter and dark matter, they are basically separately could interact among themselves, but not so much with each other.
Yeah,
So
zero. Here, just gravitationally.
do I imagine it right that essentially you have like two stars, like
Yes.
two components, fluids superimposed onto each other?
Yes.
So in that case, wouldn't there be a possibility of having drastically different collective modes, which are essentially almost decoupled from each other in the dark matter substar
they're-
and the big star, and then basically having some, maybe even kind of moving around the whole neutron
That's a
star?
very, very interesting question, actually. So the point is that when you ask about stability, for instance, this is an issue, right? So what we did, so I didn't go to the details, what we did is like perturb one fluid, and then this guy perturbs gravitationally the other fluid. We're not doing simultaneous things. But I haven't thought about this in terms even of like transport and deformations and stuff like this. This is a very interesting question. Yes, you're fully right. I agree completely with the interpretation. Yes.
Okay, thanks.
Hmm? No. Because there's no confinement for dark matter, right? It's just fermions, just you want to put a bag on what grounds? Based on what grounds?
You are groundless, and hundreds assumptions would be. This is just one more. 101.
No. That's not true. That's not fair, right? So what assumptions are crazy here, in your opinion? If you say that, you have to give the examples, right? No, I don't believe the numbers. Yeah, the numbers, the exact numbers. But I believe the trends. I believe the trends.
It's a simple question. What will happen if you confine this dark matter?
I have no idea. Huh? No, billion dark matter. Yeah, I don't know. It's just one of the simplest dark matter models that would be useful for making a star. Yeah, I know. But I would have no motivation. You still have to convince me that there is a motivation to do that.
Let's move.
Well, when you include magnetic field effects in the equation of state, you have like different pressures parallel and
Yes.
perpendicular to the axis.
Yes.
It's a problem when you...
If I keep the field up to the numbers I consider, it's a minor difference.
Oh, okay.
If I go beyond, then it becomes relevant.
So you
Then I would have to include the difference.
have just one pressure that you feed in
Yes.
the
Yes.
TOV.
It's
So
an approximation. Yeah, it's a
Yeah,
good one
that's-
up to a given field. Yeah.
Let me make a small commentary. We have already some procedures. I couldn't talk about the mathematical details as it's code available there that you feed in the equation of state at zero magnetic fields, and it solves together the Einstein equation and the Maxwell equations, and gives you the magnetic field profile of like the stable hydrostatic equilibrium. It's called Lord N. I don't know if you are aware. So, well, that's
I'll be happy to look at that. Yeah.
Yeah. Then you could take the equation of state, and it will solve already taking into account like the profile of the magnetic field that won't violate the Maxwell equations. So I suggest you to look at that. Maybe a nice improvement.
Okay.
Eduardo, well, I don't know much about dark matter, but in the literature...
I don't either.
Huh?
I don't know much either.
Well,
Nobody knows much, I think.
yeah, but in the literature I used to see any kind of dark matter, boson dark matter, charged boson dark matter, pseudoscalar, a lot of...
Yes.
Why did you choose fermion dark matter? Do you need the pressure of because of Pauli
to be able to
repulsion
make
or
a star?
something like that?
Yeah, I need fermion repulsion, right? Even for free fermions. I need Fermi pressure.
Yeah,
They
you need the Fermi-
generate Fermi pressure.
Yeah. If and this model,
Pauli
there's
blocking.
coexistence in quark matter with dark matter, or it's like a core of dark matter?
No, it's two fluids, right?
Two fluid coexisting.
It's two fluids.
Yeah.
I mean, there's no consistency problem because, these guys are totally independent in a way, right? You have it's the same thing as like having dark matter around galaxies, right? It's like two fluids. I mean, it's a fluid of stars and a fluid of dark matter.
And yeah, they coexist.
I don't see any inconsistency in this sense. I mean, the equations of state are separate, right?
No, okay.
They're not put together. It's not like a bunch of guys who interact among themselves and I have to take all this into account, right?
Yeah, but they have an effective radius of action.
Yes.
Yeah.
Exactly.
Okay.
Which is going to be like this because they're fermions. And then I could make a star just of dark matter, as I showed, right? So
Yeah.
you can make stars purely by fermionic dark matter with no problem, right?
Okay.
If you do it with bosons, then it's kind of tough. You have to invent a few things to stabilize this guy.
Also condensate of dark matter, something like that. Okay, thanks.
You show a plot of the effect of magnetic field and even dark matter when you change the central density, please.
Like this one? No,
This is compactness.
Right.
Some of these that you show
Like
for
this?
me. Now I want to see the equation of state.
So the equation of state is going to be on a
I don't
different
know.
slide.
Or maybe the mass over R.
The equation of state is this?
No, not
Or
this
this?
one.
Oh, P versus E, the plot, you mean?
Yes, because what I'm saying is that
Yeah, but that's with magnetic
I
field.
gave a talk here, and I really would like to, there, 400, you show, there, 400.
Yeah, this is
Yes,
for
yes.
magnetic field.
Yeah, so you see, if you are changing, okay, with 210 to 8, 210 to 8, sorry, but you have already parallel pressure blast, very different from
Yeah, we can
so
check
2
the
you cannot
references.
go. No, you cannot go. You can go just, as you said, 10 to 18 maximum, okay? Because if not, you are changing. What you are doing, you are putting energy, magnetic energy in your system. If you are putting magnetic energy, you are putting pressure magnetic. So you are changing really your star. So no way to do spherical symmetry, sorry. So it's why you are getting...
You show me your
is
paper,
this
I show you the
this
paper
plot
I'm
here?
making, right?
Yeah, this plot you show is
Yes.
written in many papers. This is no sense, that plot, because this reduction of the radius that comes because you have a much more dense system, okay, is a spherical star, and the star is not spherical for all. So this is no... So you need to think that if you want to change, you need to go, as the people go, to cylindrical metric, okay? No way. So, I don't know, because if not, you say, what you say that is small? Is what, 30% is small, 20% of radius, that
No, it's less than that.
equatorial radius
Yes.
change from this. In fact, so all the results you have for tidal deformability, that depends on compactness. It's only compactness. If you have different radius, okay, and you have smaller here than here, does not make sense even that number. So I should say that magnetic fields, if it's not for weak interaction things, okay, but like you are doing is for changing really equation of state of, how can I say, QCD or nuclear, no way to do spherical. So if not, you, I don't know, you will say, or maybe you say 30%.
Can I stop so that I can reply? So please stop that I can reply.
I can do the calculation for you now.
Yeah, you can do it. So show me your results, and I'll show the results I'm using, right? Which are good for exactly this number. So people have computed this. So the paper that I'm using to get this number here is a paper by Dirk Rishke and Ahmed Sedrak and someone else, Han. And so I can show you the results, and you show my results. And then we agree or we disagree, right? I think you're wrong, and you think I'm wrong.
Yeah, we have to move on
Up
because
to
we still
2,
have
it's
questions
okay.
and we have a little bit late
Beyond,
too.
it's not okay.
This gives 400, and if you prefer, with 2 times 1018, it's only square it and divide by 8 pi.
Okay.
Yeah.
Yes.
Yeah,
yes.
Kenji had a question.
May I? Yes. Okay. So yeah, my question is about something you said you didn't care, but you said you didn't care. That is interaction. But I know that some people care.
Oh, interaction between dark matter and
yes. Okay, so you know the Chris Kubaris and Hamaguchi and many beyond the standard model people care about that, and that is a dark matter capture by moving a neutron star, and they propose that the cooling curve is significantly changed, and it is
what would change? Sorry,
the cooling curve.
Oh, okay.
Okay, because it is heated up by the capture of the dark matter.
Right.
Anyway, so it is really interesting to see that even the neutron star structure is such changed by the effect of the dark matter. And if the dark matter capture is taken into account, then the mass has also some evolution, right?
Yes.
So it gives you some extra effect on top of some standard scenario of mass accretion and so on and so on. So by looking at some the evolution of some neutron star,
that's interesting.
by making some comparison to some standard model, so is it possible to say something also about the existence of a dark matter? Or?
Maybe.
If you care.
I'm not aware of this reference that you mentioned. I'm curious to see. So the only things that I've seen is some expectation of accretion of dark matter, but very naive ones usually. And so they have to assume there is a non-zero cross-section so that you can really accrete. Yeah, then you can compute the flow of dark matter crossing the neutron star, and then, okay, but I haven't considered anything dynamical like this.
Let's thank Eduardo again. We have to go to the next talk.
Thank you.